Okay, so now here we're at problem 7, and problem 7 relates to buffers, okay, which I know that you had to make in lab. And problem 7 is a great example of how buffers actually work. So we are going to examine that. And we've already talked about the Henderson-Hasselbalch equation. We're going to apply that when we solve for this. But we're going to go step by step, okay? So here's what we got. The question is, what is the pH of a solution containing 0.1 molar in both HNO2, which is a weak acid, and NaNO2 after the addition of some acid and some base? So before we start talking about adding anything, let's consider what we have to begin with the buffer. So the buffer, a buffer always has weak acid and a salt. The weak acid partially dissociates, and the salt forms conjugate base. It is a strong electrolyte, which means that it fully dissociates. And I jumped a little bit by saying it makes this conjugate base. So here, for a buffer, we have a weak acid and we have a salt. The weak acid has the anion plus the proton on there. The salt has an alkali metal as the cation, and then it has NO2 as the anion. So we have the same anion. That's also important when we talk about buffers, okay? Same anion, one of them is a weak acid, the other one is a salt, which eventually forms a conjugate base. The weak acid partially dissociates, the salt fully dissociates. All right, so the first step in all this is to calculate the pH of the buffer, which is 0.1 molar HNO2 and 0.1 molar NaNO2. So let's figure that out. And we need some information, or at least we need to think about some information in order to solve for that. Where's my, okay. So let's remember the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation, again, is pH is equal to pKa, talking about acids, plus the log of conjugate base over the acid. All right, so we have that information. Now, we know that the Ka was given. So, for solving this, Ka is equal to 4.5 times 10 to the minus 4. So the pKa is equal to the negative log of 4.5 times 10 to the minus 4. And we have that value because we just calculated it in the previous problem, right? Or not, yeah, previous problem, which is 3.35. So we have that information. Now we need the other stuff. So let's look at putting information in. So for the Henderson-Hasselbalch equation, we have pH is equal to 3.35 plus the log of conjugate base over conjugate or over acid. All right, so what's that? What happens? Let's take a look at what we've got. We've got weak acid that partially dissociates, and we have strong electrolyte that fully dissociates. Let's look at the reaction or dissociation reaction of the salt, the sodium nitrite. So sodium nitrite, NaNO2, nope, minus right here, fully dissociates in water to form Na plus and NO2 minus. We start with 0.1 molar of sodium nitrite. So initially we have 0.1 molar. We don't have anything that's formed. The change is that this fully dissociates, so it'd be negative 0.1 plus 0.1 and plus 0.1, right? All the way across, which then gives us the equilibrium concentrations of 0 for the salt. It's not staying together. It's fully dissociated to give 0.1 molar of the sodium ion and 0.1 molar of NO2 minus. Well, the other equation involved is for this weak acid, which would be HNO2 partially dissociating to be H plus NO2. So the same thing. So we have this reaction that's happened, and we have this that is happening. Okay? This is acid, this is H plus, and this is conjugate base. So when we are solving for the pH for the Henderson-Hasselbalch equation, we're going to be putting the log in of NO2 minus over the concentration of HNO2 initially, okay? So we're going to apply these here. So what we have thus far is all of the information that we need, actually, because we know that, rewriting this, 3.35 plus the log, but we have the concentration of conjugate base, because like I said, there are two equations that are taking place, two reactions, dissociation reactions. There's this one and this one. This one reacts with conjugate, or dissociates to form conjugate base. This one forms conjugate base because of the dissociation of the salt. So then the concentration of conjugate base that we're starting with is 0.1. So that means that we can then insert 0.1 in for the concentration of conjugate base. And we started with 0.1 molar for weak acid, so we end up with this equation. Now we see that these cancel out, and we end up with an initial pH of 3.35. So this is the initial pH of the buffer, which is similar to problem 6, where we added just some negative conjugate base. We added some negative, or some anion, some NO2 minus, it's the same thing. It ends up being where we have 0.1 over 0.1, and then it gives us a pH of 3.35. We just know that now that supply of for the increased number of anions comes from the presence of the salt being here for the buffer. Okay, so this is our initial pH of buffer. Now that we know initially, our next step is then to consider what happens when we add some acid to it. So let's do that. So this would be step 2.